Okay, so we are still discussing in our textbook, chapter 11, so the theory of series. Now, today we are going to discuss some part of the theory, which is actually one of the reasons why we consider series. Now, just to remind you, so last time we introduced so-called power series. Now, what is a power series? So a power series is a series of the following form. So you have a series over an and then x minus a to the n. So this is called a power series. So somehow you can think about it as you can think about this function which you get here as a generalization of polynomials. Okay, because if you look here at the partial sums, then what you get is a polynomial, and what you get here as a sum function can be considered as a generalized version of a polynomial. Now, last time we saw already that the convergence behavior of such a power series is rather special, in the sense that either the power series converges for only for x is equal to a, or the power series converges for all x, or the power series converges for x which are in an interval which is centered at a. Okay, so there are only three possible cases. So normally the domain of this function here will look like something like, okay, normally we will have an interval. So we will have something, if we look at all the real numbers, and we have here a, then normally we will have a radius of convergence r, and the power series will converge inside this interval here, and outside this interval the power series will diverge, and at the two boundary points everything can happen. We saw last time examples for this, but the domain of this function typically is such an interval. Okay, but the r can also be equal to 0. In this case, the interval just shrinks to one point, and the r can also be equal to infinity. Then the interval extends to all real numbers. Okay. So last time we discussed this special type of power series, this class of special class of series called power series, and last time I already explained roughly why this class of series is important. Namely, you can look at those functions as generalizations of polynomials. Okay. Now today, so for instance, or before I talk what we are going to do today, let's maybe look at an example. So the most easiest example for such a power series is the following one, which you have already learned in high school, geometric series. Okay, and here this is the function f of x. We all know is 1 over 1 minus x, and we have convergence for all x in the open interval from -1 to 1. So the radius of convergence for this example here would be equal to 1. Okay, and and the power, and you can look at this as a power series which is centered at a is equal to 0. Okay. Now the main thing what we want to do today, and maybe also next time, is to reverse this kind of thing. Okay. So what do I mean by reversing? What we want to do is, okay, I give you a function like this one, and we try to find a power series which represents the function. Okay. So last time we had given the power series, okay, we tried to figure out for which x is the power series convergent, and we haven't done this last time, but of course the next question would be, okay, what is this function here? Can you find an expression for this function? Now, today we are going to, as already said, so today we are going to discuss the inverse question, namely, given a function, okay, how to find a power series which represents the function on some domain. Okay. Now you might ask, okay, why are we interested in this question? So why are we interested for a given function to write it as a power series. There are many answers to this question. The most simplest question is because a power series, as I said here, is somehow an extension of a polynomial. Okay. In particular, you can use this series here. So if you just look at the first n terms, you can use this in order to approximate the function. So you will get a way to compute f of x. Okay. Which is important for some functions where we have never discussed how to compute them, like sine of x or e to the x and so on. And actually, the calculator is doing the computation like this. Now, our main problem is, okay, given a function, so given f of x, okay, so find a power series representation Okay, so what do I mean by this? Okay, so this means write f of x in the following form. So as a power series, a suitable power series, a n x minus a to the n. Normally the a here is given. Okay, so normally you have given, for instance, you have a given function f of x. Find the power series centered at the given a. So for instance, if I give you this function and I ask you to find the power series representation centered at 0, okay, here is the answer. Okay, but how about other values for a? So for instance, I give you this function and I want to have the power series centered at 2. Okay, so is it possible also to give a power series for this case? Now, this kind of general question, this general problem, okay, already entails a couple of questions. So what are good questions here? So obviously the first question is, okay, if I give you a function f of x, how can you see that there exists something like this? So maybe it's not possible to write f of x like this. Okay, so how can you see that f of x has a power series representation just by looking at f of x? This is a question we have to consider. Then if you have some general tools or some general results which tell you that for certain f of x, just by looking at them, you know, okay, this function f of x has a power series representation. The natural next question is, okay, how to find it? Okay, and the third question would be, okay, for instance, for this example here. So here you see the power series representation of this function at x is equal to centered at a is equal to 0. Okay, the third question would be, okay, is there another one? Okay, or is the power series representation unique in the sense that if I cannot find, except of this one, I cannot find another one which also represents the function and is also centered at 0. So is this process unique? Okay, and essentially what we are going to do today and next time is to answer those three questions. Now, before we go into a general theory, because there exists a general theory which tells you, okay, for which functions f of x do you have a power series representation, how to find it, and so on. Before we go into the general theory, we look at some special examples, because, for instance, for this function, obviously, we can find the power series representation, because we know already that this power series converges to this function. Now, let's use this as a starting point for other examples. So, for instance, if you look at something like this here, so if I give you the function this one, okay, of course you can use the same series, okay, and you will get also a power series representation for this one. So here it's easy to find a power series representation. Now, always I discuss at the beginning always the case a is equal to 0. If I do not look at the case a is equal to 0, okay, I will point it out. So I'm interested in a power series centered at the origin a is equal to 0. Now for this case, of course, it's easy because you just use this here, but you replace x by x to the 4th. So you have to the sum n from 0 to infinity. And the only difference is, okay, you have this function here. But this is also a power series. You see this has this form here. Okay. So I found already for this function here a power series representation. And where is this valid? Of course, the the domain where this is valid, okay, it's just the same as this here, but x replaced by x to the fourth, but this doesn't make any difference. So you see that this is also valid in this interval here. Okay, so this is one case. Now, maybe a slightly more complicated example is this one, x to the 4x plus 1. Okay, so now here, how to find a power series representation is also not very complicated. Okay, I look at it like this here, x over 1 minus 4x. And now I use, again, this result here. So I have x times, and then this is the sum n from 0 to infinity, minus 1 to the n, 4 to the n, x to the n. Okay, so the power series here becomes the sum n from 0 to infinity, minus 1. Sorry, this is n to the n, and then 4 to the n, x to the n plus 1. Okay, and it is valid for all x. So I just have to look at the domain of this power series representation. So it's valid for absolute value of 4x is smaller than 1. Okay, which is equivalent to the absolute value of x is smaller than 1 over 4. So here we have just the interval from minus 1 over 4 to 1 over 4. Of course, the question could also be different. For instance, I look at this function here, f of x 1 over 1 minus x. But now I'm not interested in the power series centered at 0, but for instance, a power series representation centered at some other point. At a is equal to, for instance, you should notice a is equal to 1 wouldn't be possible. Okay, for a is equal to 1, it's of course not possible to find a power series representation because this function is not defined at 1. Okay, but okay, so how about the case a is equal to 2? Okay, now how to find the power series representation of this function given that a is equal to 2? I just use the same idea as the idea you have seen here already. So I write this function 1 over 1 minus x. So what I want to have is 1 over, and what I want to have here is minus x minus 2. Okay, and then I use the same idea. So I have to subtract minus 1. And now, okay, so actually, okay, so actually I take out the minus. Okay, and then for the rest, I have to sum n from 0 to infinity, and then minus 1 to the n, x minus 2 to the n. Okay, and now I have a power series representation for this function f of x centered at a is equal to 2. Okay, and this is valid for x with now. I just have to look at this here. So the absolute value of x minus 2 smaller than 1. Okay, so this is the interval from 1 to 3. Okay, so you understand what I'm interested in. I'm interested in given a function. Okay, I want to find given a function and the point a, I want to find the power series representation. Okay, here you see some examples. Now, so all these examples here are based on the geometric series, on the most easiest series we have encountered here. Now, from the geometric series, we can also derive a couple of other more interesting examples by using the following result, which you find in our textbook. Okay, so assume you have given a power series. Any questions? Huh? But here we have another minus. So actually, okay. Yeah, okay. Okay, so assume we have the following power series. Assume this is a convergent power series with radius of convergence R. Now, so this means you have a function f of x, and this function has its domain at least the interval from a minus r to a plus r. Now, this theorem tells us that this function f of x has some special properties. So if you have these assumptions here, then f of x is differentiable on the interval a minus r, a plus r, and now you have two properties. So first of all, the derivative of this function has also a power series representation, and the power series representation is this one. So the one you would expect, n a n x minus a to the n minus 1. And second, because f of x is differentiable, so f of x is also continuous. So also the integral of f of x dx, also this function here has a power series representation, and you compute it just by an, and then you have x minus a to the n plus 1 over n plus 1 plus a constant. Okay. Moreover, the power series in 1 and 2 have radius of convergence R as well. Okay, so what does this mean? Okay, so you have here we have given a function, okay, which is represented by a power series which is centered at a. Okay, now this theorem claims is that this function here, okay, under this condition, so if this function is equal to this power series, must be differentiable, and the derivative and the integral both have a power series representation as well. Okay, and you get this power series very easily from this power series by what we call term-by-term differentiation, and here, so here term-by-term differentiation, and here term-by-term integration. Moreover, this power series representation, you see here, those two power series representations are also valid on at least this interval here. Okay, and this the radius of convergence of those two here is equal to r to the original one. Okay, now if you look at something like this here, okay, and you take derivatives on the left and right hand side, okay, you will say, okay, of course this will be true. Okay, you just take the derivative here. Okay, here the same, you take the derivative. Okay, so if you interchange the series and derivative, okay, you will you just compute the derivative here, and that's it. Okay. Now, something which is important for series, okay, is that the crucial step here, and this is why we need a theorem, is okay, if you take the derivative here, okay, so you have to take the derivative here. you have to interchange the derivative and the series. Okay. Now, if we have a finite number of functions, we know that if we have two functions, we know that the derivative of f plus g is the derivative of f plus the derivative of g. But here you have an infinite sum of functions. Okay, and it's not true for every. So whenever you have here a series, okay, which depends on some x, okay, it's not always true that you are allowed to interchange differentiation and the series. Okay, but this theorem tells you that if you have a power series, then you can do this. Then this is true. Okay, this is a very important remark. You will encounter many situations in the next few years, okay, where you actually have to do this, okay, where you have to interchange differentiation and a series, okay, and normally you have to be careful in doing something like this, okay. You will see in applied classes that normally not so much care is taken in interchanging, okay, and this is a common mistake in even in papers written by non-mathematicians. So papers which are like related to engineering and so on, I see very often this that it's not discussed whether it's allowed to interchange differentiation and series, and sometimes it's wrong to do it. Okay. But here in this situation, there's no problem. Okay. So if we have a power series, we can very conveniently, okay, we can differentiate this one, okay, and this will be equal to the term-by-term derivative of the series, and for the integration the same. So you can interchange integration and series, okay, no problem. Okay, so but for us at the moment, the important thing is that if you have a power series representation for a function, okay, then you automatically immediately get a power series representation for the derivative of the function and for the integral of the function as well. Okay, so any questions to this result? We are not going to prove it. You also do not find the proof in our textbook. Okay, the proof is not so complicated, but if you are interested, you have to look at more advanced textbooks on calculus. But this will be a very important result for us. Now, maybe I should also stress that if you look at this power series, okay, and you take the the power series which you obtain by term differentiation, so this one, okay, so those two power series, this one and this one, have the same radius of convergence, okay, but not necessarily the same interval of convergence, which means that okay, so this if this power series has radius of convergence r and maybe interval of convergence, the closed interval from a minus r to a plus r. So for instance, it could be that this power series has the closed interval here as interval of convergence. This might change for the derivative. Okay, so for the derivative, it might be possible that it's the open. Okay, so at the boundary, only the two boundary points, something can happen by taking derivatives. We will see some examples where this. Now, this is something very convenient because using this, for instance, if I give you the function f of x is equal to 1 minus x squared, okay, and I'm interested in a power series representation centered at the origin at a is equal to 0, okay, for this function, then you see, okay, you only have to recognize that this function is the derivative of this function. Okay, so this is what you have to recognize, because for this function here, we know the power series representation. Okay, so this is d over dx, and then here sum n from 0 to infinity, x to the n. Okay, so by the theorem which I showed you, okay, we are allowed to interchange differentiation and the series. So what we get is a series n from 1 to infinity, n x to the n minus 1. Okay, so and we have, this means we have found a power series representation of this function here, namely this one. Okay, so where is it valid? We know that because because this representation, this power series representation here, or if you look at it from the other way around, this power series has radius of convergence 1. Okay, so this power series will have radius of convergence 1 as well. Okay, so the radius of convergence of this power series is 1. Now, but as I have emphasized, the interval of convergence might change. So we have to check the two boundary points, x is equal to 1, but obviously divergent at x is equal to 1, and also divergent at x is equal to -1. Okay, so this one is, this power series representation is valid on this open interval from -1 to 1. Okay, so you see that this is also the interval of convergence of this power series. So this means, for this example, if I differentiate not only term by term, if I look at the term by at the series which I obtain by term differentiation, not only the radius of convergence remain the same, but also the interval of convergence remain the same. For this example here. Okay, so this is one example. Now, maybe a more interesting example is this one. So let's look at this function, ln 1 minus x. Okay. Note that ln of x does not have a power series representation at 0, okay, because it's not defined at 0. But this function here has a power series representation at 0, and again we are interested in, okay, what is the power series representation at 0? Now, here you have to realize that, okay, you can write this function as okay, minus the integral dx over 1 minus x. Okay, so this is what you have to recognize. Okay, because if you take the derivative here of this function here, you see it's almost this function here, except of a minus. Okay, so in other words, this function is the integral of more or less this function here. And again now, for this function we already know a power series representation, so we have here the sum n from 0 to infinity x to the n dx. Okay, and now we know by our theorem we can use here term by term integration. Okay, so we have the series n from 0 to infinity, and if we integrate this term by term, then we get x of n to x to the n plus 1 over n plus 1. Actually, we have plus a constant. Okay. Now, but you see that, first of all, we know by our result that this will be true for at least for x inside this interval. Okay, this is what our result is saying. So you have this power series representation of ln 1 minus x at least on this interval here. The constant c is easy to determine because you see if you plug in x is equal to 0, where this relation is satisfied, then you get here 0. So c is equal to 0. Okay, you just plug in x is equal to 0. You see this is 0, this is 0. C must be equal to 0. Okay. Now, this series and this series have the same radius of convergence by our result. How about the interval of convergence? For this series, the interval of convergence is this one. But for this series, you see that if you plug in n is equal to 1, okay, then if you plug in x is equal to 1, so the right boundary, then you see what you get is a divergent series. If you plug in x is equal to -1, what you see here is a convergent series. Okay, so you see here, this is an example where if you have given a series, a power series, you look at the power series which is obtained by term integration. That's also the radius of convergence must remain the same, but the interval of convergence is different. Here the interval of convergence is this one, and here the interval of convergence is the half open interval, -1 included, to 1. Okay, so you also see here you can actually shift you can actually shift the index here, so you can go n from 1 to infinity, x to the n over n. Okay, Sometimes also written in this form here. This is the one I normally prefer. Okay, this is already a very important power series representation. We can memorize it. Now for x in this interval. Okay, so we know that this is valid here. This equality for x in this interval. Okay, from the theorem I just showed you. Okay, but we know that actually this series here is convergent for x is equal to -1 as well. Okay, so this here is convergent for x is equal to -1 as well. And what is the series here? So we plug in -1 to the n over n. But for this point, also this series is convergent. It's not necessarily from the theorem you just saw. We do not get that here is equality. Okay. But if you look at this one, okay, then you see, okay, this is -1 plus 1/2 minus and so on. We have studied this series. We know this is minus ln of 2. Okay, and minus ln of 2 is the left-hand side. So actually, also at this point, okay, the equality holds. Okay, but not. I should stress once more, not from the theorem. Okay, we get this from the by directly checking. Okay, right and left-hand side. Okay, so actually. This is true not only for this interval, but even so this here holds on this interval from -1 to 1. Okay. Now one more example. How about the arctangent of x? Okay, so how about this function? Again, I'm interested in the power series representation of this function at x is equal to 0. Okay, and again, the theorem I just showed you is useful because we all know the arctangent of x is equal to the integral dx over 1 plus x squared. And here, this function, okay, we can find the power series representation. So we have the integral, and then sum n from 0 to infinity, -1 to the n x to the 2n dx. Okay. Now, again, we can use our result. So this integral we can compute by term integration. Okay, so -1 to the n x to the 2n plus 1 over 2n plus 1 plus a constant. Okay, the constant, so this is valid because this power series representation inside the integral is valid on the open interval. So this here is valid on the open interval from -1 to 1. Okay, so this will be valid also on the open interval -1 to 1. This is what we get from our theorem. Now again, if we plug in x is equal to 0, we see c must be equal to 0. Okay, so because if you plug in here x is equal to 0, you have here 0, you have here 0, so c must be equal to 0. And you see that actually this series here, okay, if you check at the two boundary points, 1 and -1, okay, so let's check x is equal to 1. Then we see we have the series -1 to the n over 2 to the over 2n plus 1, and this is an alternating series. Okay, maybe I should write this slowly. Okay, so I want to check the two boundary points. X is equal to 1. So for this, only for this series here. So for this point, we have here the series n from 0 to infinity -1 to the n 1 over 2n plus 1. Okay, this series convergent because of the alternating series test. Okay, and how about x is equal to -1? Now for this, you get almost the same series. Okay, because here you have a -1, so what you get is this one. Okay, and because of the same reason, it's convergent. Okay, so this series also remains convergent at the two boundary points -1 and 1. Okay. Now, again, it would be interesting to know whether this representation you see here, because from our theorem we do not get that this representation is true as well for x is equal to -1 and 1. Okay. It's not so complicated. Maybe one of the home assignments. It's not so complicated to prove that this representation you see here holds as well for, holds as well for, in those two cases, x is equal to ±1. Also for this case, it can be proved that you still have an equality here. And the case x is equal to 1 is in particular interesting. Okay, because if you plug in x is equal to 1, you see what you get is pi over 4 on the left-hand side. And on the right-hand side, you get the series -1 to the n over 2n plus 1. So what you get is 1. This is equal to 1 minus 1 over 3 plus 1 over 5 minus 1 over 7 plus 1 over 9 minus 1 over 11 and so on. Okay, it's a nice way to. It's a nice identity. Could be used to compute pi. Okay, up to some digits. Unfortunately, the convergence here of this series is not very quick. So if you really want to compute pi up to many places, you have to do many computations here in order to find pi. And this is not the best method to find pi. Okay, this is better than the most primitive method you maybe have discussed in high school, where you have a circle and you inscribe n polygons and subscribe n polygons, and then you approximate the circumference of the circle like this, and then you divide. If it's the unit circle, just half of it, and you have pi. This was the method which was used by Archimedes 3,000 years ago, which is not the best method to compute pi. This here gives you not a good method, but at least another method to compute pi. So you forget about, for instance, you take the first 100 terms here and you add them up, the first 100 terms, you multiply by 4 and you get an approximation for pi. Okay. This is actually a famous formula called Leibniz formula for pi. It's a nice formula. Now, actually, I haven't discussed the question yet why I'm interested in representing functions by power series. Okay. Now, I gave you one reason for this, namely, if I know a power series representation for a function, I have a way to compute the function. Or you see, if you evaluate the power series representation at certain points, you can also find constants like pi and so on. So if you have given a function f of x, and you can find a power series representation, so you can write the function here like this. Okay, then you have a way to compute the function for certain x. You just take this here. You take the first n terms, you add them up, and you use this as approximation for the function. So this is one reason why we are interested in representing functions, complicated functions, as power series. Power series is some kind of easier than more complicated functions. Another reason is we have seen already last semester that some integrals we can either not compute because, for instance, this guy here. Okay, we cannot compute this integral here, or I should say it can be even proved that this integral cannot be written in our standard functions. Okay, but we know from the fundamental theorem of calculus, because this is a continuous function, we know that the antiderivative of e to the minus x squared indeed exists. Okay, now we will see that one way to compute in a different sense. Okay, this integral here will be using power series representation. So what you do is you find the power series representation of this function, you plug it in, and then you use term-by-term integration, and that's it. Then you get an answer, but the answer, you maybe might say, okay, the answer is not what you wanted to have. You would like to have this integral in terms of the function, expressed in terms of the function you know. Okay, so, like logarithmic functions, exponential functions, and so on. Some expression. It's not possible. Okay, but like this, we are able to write this the antiderivative of e to the minus x squared as a power series, and this helps then in computation in computing, for instance, certain values of this integral, like this integral here. Okay, so this would be for a function where we do not know. Or where we do not have an expression for the antiderivative, but this can also be used for functions where we actually have a method to integrate them, but it would be the expression you get is not so nice. For instance, if you have this example here, we have a method to compute the antiderivative, but you know, you first have to factorize the denominator and so on. So it's, for this example, it would be quite a lot of work, okay, to do it. Now, a much easier way to do it, in particular, if you do not have access to a computer algebra program like Maple, because if you have Maple, then it's easy. You just plug it in, and Maple will give you the answer. But if you do not have access to a program like Maple, then you might be still interested in knowing the value of this integral here up to a certain precision, so up to a certain certain number of digits. Okay, and this is indeed possible because you we know that this function here, you see 1 over 1 plus x to the 7 has this power series representation minus 1 to the n x to the 7n. Now, by our results, okay, we can interchange integration. Maybe let's forget first about the upper and lower limit. So we can interchange integration and summation. So we have minus 1 to the n, then x to the 7n plus 1 over 7n plus 1 plus a constant. And now if we are interested in the definite integral, which I showed you at the beginning. Okay, so we just have this is the antiderivative of the function, and we have to evaluate. We do not have to take the c into account because it's just enough to know one antiderivative. This is 1, and evaluate at 0 and 1. Okay, so what you get is minus 1 to the n, and then 1 over. And this is indeed helpful in order to compute this integral, because we know that, okay, first of all, this is a series. Okay, so there is the natural way to compute the sum of this series. Namely, you just take the first, let's say, 100 terms, you sum them up, and take this as an approximation. But moreover, because this is an alternating series, we have very good control over the error. Okay, we know that the error is just the first term we drop. Okay, so actually this also helps us. So if you go up to a capital N, then the error will be bounded by 1 over 7n plus 1 plus 1. Okay, and this will help us to choose the n large enough such that we get the value of this integral up to a certain precision. So this is very helpful, and you see that. You can say that this here is the antiderivative of this one. Okay, it's maybe not what you. It's maybe not the way you wanted to have the antiderivative. Maybe you want to see an expression for it. Okay, but if you are familiar with power series, okay, this is an answer as well. And from the computational point of view, is acceptable because you can compute the value of this integral up to an arbitrary precision. So you see, this is one motivation as well why we look at, why we are interested in representing given functions as power series. It will make the task of integration much, much easier. You see in our textbook, this is an example of our textbook. You see that if I do not look at this here, but I look at the integral, this is somehow more easier to compute from 0 to 0.5 of dx over 1 plus x to the 7. So you see that using the same reasoning, you get the series, and then minus 1 to the n, and then you have here 0.5 to the 7n plus 1 over 7n plus 1. Okay, and because what you have here is something which is smaller than 1, okay, as n is getting large, this will go to 0 very, very quickly. Okay, so for instance, if you look at n is equal to 4, okay, so which means you take here the first 5 terms, then your error, this is, I take the first 4 terms here, so I use from 0 to 3, then the error is bounded by the 4th term, okay, and the 4th term here is 1 over, you see here this is 29, and then you have here 0.5 or 2 to the 29. Okay, and this is something which is very, very small. Okay, this is 6.4 times 10 to the minus 11. Okay, so this means if I take here the first 4 terms, 0, 1, 2, and 3, okay, you already get a very, very good approximation of this integral here. So then you get this is equal to 0.4995137.4, and this error bound tells you that all those digits here are already correct. Okay, so you see, once we understand how to find power series representation of given function, this will be a very powerful tool. Also, this will also simplify, in this sense, the task of integration. And there are also other advantages which I cannot explain at the moment because we haven't talked about. Maybe you have encountered already in some other classes differential equations which involve the derivatives of functions. Such equations, many of them are not. It's not possible to find a closed solution, a closed form solution, some expression for the function, and also for such equations, first, assuming that f of x is a power series representation, allows one to solve them much more easily. I guess you will have a course on differential equations maybe next year. Then you will encounter this once more. Okay, but you saw in this section we just discussed special cases. So in particular, all our examples. So we know now a power series representation for ln 1 minus x. We know a power series representation of the arctangent of x. We also can find the power series representation of functions like 1 over 1 minus x in brackets square. We just take but all those power series representations are all based on the geometric series. Namely, we know that 1 plus x squared and so on is equal to 1 over 1 minus x. You see, just looking at this example, we already can go pretty far. Now, as I told you at the beginning, actually we are interested in a general problem. The general problem means, okay, any functions, I give you any function. For instance, I give you e to the x times sine of x, okay, or tangent of x. Any function. We are interested in figuring out, okay, the first question is there a power series representation? Yes or no? And once you can answer this question, okay, how to find it? And the third question, which will be important, is it unique? Okay, or are there other ways of representing a given function as a power series? Now, actually, the question which we answer first is the last one. The question whether it's unique or not. Okay, so the question we want to discuss first is a power series representation unique? Okay, so assume you have given a function f of x, and we already know we can represent the function f of x as the following power series, an x minus a to the n. Okay, and let's say this power series representation is valid for x with the absolute value of x minus a is smaller than, let's say, d. Okay, this maybe I should stress this because maybe at the beginning this is a little bit confusing. Of course I know. Of course we know that this power series has a radius of convergence. Okay, and if the x is outside the radius of convergence, okay, there's no chance that you have such an equality because this thing here does not exist. Okay, so if you have such a power series representation, okay, this power series representation can be valid at most on the interval of convergence of this series here. Okay, but for a given function, okay, it's not necessary that that the power series representation is once it's valid. It's not necessary that it's valid on the whole interval of convergence. Okay, could be a subinterval. Okay, so this is what you should understand here. That's why I write here d. This d, of course, must be smaller or equal than the, or smaller, at least smaller than the radius of convergence. Okay, because if you are outside the radius of convergence, no chance, because this object does not exist. Okay. Now, so we assume that we have given a f of x, and we already know there is a power series representation. Okay, on some interval around a. Okay. Now, if we know this, okay, what can we say? We can say because of the theorem I showed you before. Okay, this is the theorem. If you wanna look it up once more in your textbook, 11.9. In section 11.9, there's only one theorem there. This theorem is very important. Okay, because of this theorem, we know that this function f of x here is differentiable. Okay. Actually, you should recognize this gives us already one condition. If a function f of x is not differentiable, no chance that there is a power series representation. Okay. So from the theorem, we get f of x is differentiable. Moreover, we know that okay, if you replace this series by the series you obtain by term differentiation, then this will be a power series representation of the derivative. Okay, so you know this will hold also for x with okay, and you can go on like this. Okay, so now you use the same way of reasoning, but now you replace the original power series representation by this one. So again, by the theorem, this function is differentiable, and the derivative you get by term by term. You take this series and term by term differentiation. Okay, so the second derivative n times n minus 1 an x minus a to the n minus 2, again for all x with. Okay, and you can go on like this. Okay, so you see that if you have given a function f of x and the function is not differentiable an infinite number of times, no chance that there is a power series representation. Okay. Now, at least on some interval, okay, it must be differentiable. If you wanna find the power series representation at a, then at least at this interval, at some interval around a, the function f of x must be differentiable infinite number of times. Otherwise, it doesn't have a power series representation. Now, but from this here, you see more. Namely, from the first one, okay, you see if you plug in x is equal to a, you see that because x is equal to a is of course a x where this is satisfied, then you get f of a is equal to a0. Now, if you look at this here and plug again x is equal to a into the relation, then you get that the derivative of a is equal to okay a1. Actually, you have 1 times a1, and here. In this case, okay, again, x is equal to a, then you get the second derivative of a is equal to 2 times 1 times a2, and you go on like this. So you see, in general, you will get that the nth derivative at a is equal to n factorial an. Okay, but this means that an is equal to the nth derivative of a divided by n factorial. And this is important because this tells you once there exists the power, if a function f of x has a power series representation, okay, it's unique because for an you have only one choice, namely this one. Okay. So you see that because normally if you ask for a power series representation, what is given is f of x and a. Okay, and you have to find something like this here, and this here tells you, okay, there is only one choice, one possible choice for an, namely this one. Okay, but the inverse is not true. Okay, if you can compute this one, okay, it's not necessarily true that you have something like this. Okay, but this tells you that now the problem is already a little bit clearer. Namely, if you want to find the power series representation of f of x, what do? You have given f of x a, what do you do first? First you compute here this sequence. Then you look at this series here. And then you check whether this series is equal to this one. Okay? And this is a systematic way how to find power series representations for a given function. Okay? So here the most important information here is the power series representation is unique. Okay, so what we know already is, okay, given a function f of x and the point a, if you wanna represent f of x as a power series representation, you have to look at what you have to look at is this series here. So the nth derivative of f at a over n factorial, n from 0 to infinity, x minus a to the n. Okay, so this is the first step, because if the function has a power series representation, that's the one. Okay, but the other way is not necessarily true. If this series here is convergent for some x, it's not necessarily true that it is equal to f of x. Okay, this is what we have to prove. Okay, now but this is at least we know now how. At least we know now how to search. Okay, how to search for the power series. We first compute this one. This must be the if f of x has a power series representation, this must be the power series represented. The power series representing f. Now, because of this importance of this power series has a special name. It's called the Taylor series. Okay, so this is called the Taylor series of f centered at a. Okay. Now, the special case where a is equal to 0, okay, which means I'm interested in a power series expansion of a function at the origin, okay, was studied earlier by Maclaurin. So this is called this special case has its own name called Maclaurin series. Okay, so given a function f of x, if you are interested in finding the power series representation, the first thing you're going to do is to find the Taylor series or Maclaurin series. Okay. The second thing which you have to do is, okay, you will discuss the radius of convergence of the Taylor series. The third thing you have to do is you have to prove that it represents the function. Okay. So for instance, if we look at the function at the special example, f of x is equal to e to the x. Now here it's very easy to. So first we have to find the Taylor series. We are interested in finding a power series representation of this function at a is equal to 0. So in other words, we are interested in representing this function in the question where can this function be represented by its Maclaurin series. Okay. So first we find the Maclaurin series. So the derivative at 0 is equal to 1. So you see that the Maclaurin series is this series here. So this is the first step. Okay, we find the Maclaurin series. The second step is we discuss the properties of the Maclaurin series. We know already from last time. Okay, maybe I recall this. Okay, so the next thing is, okay, we are interested in, okay, where is the Maclaurin series defined? Okay, so we will look at the radius of convergence, which is here easily computed by using the ratio test. So we can take out the square root of absolute value of x, and then we have the limit n tends to infinity 1 over n plus 1, which is very fortunate because this is always equal to 0. Okay, 0 is smaller than 1, so we know, okay, the radius of convergence of this series will be the set of real numbers. Okay, so in other words, this series is defined for all x in R. Okay, and now the third step, okay, would be, okay, the third question we have to answer is the question, okay, is it true that this holds here, and if yes, where? Okay, it's not necessarily, because we know that this object is defined, okay, for all x in R, okay, but it's not necessary that you have the equality for all x in R. Okay, so we have to figure out, okay, for some x, for x at least. Okay, so what is the d? Okay, or is it even true for all x, such that this relation here holds? Okay, of course you always have at least for the point, okay, at which the Maclaurin series is centered. Okay, this relation is of course true. Okay, so the question becomes, okay, for other points, is it true for other points as well? Okay, now here you already see, okay, if you have given a function, how to find in general the power series representation. Okay, so the first step is find the Maclaurin. If let's assume that the power series representation we ask for is always centered at a is equal to 0. The first step is, okay, find the Maclaurin series. Okay, the second step is discuss the convergence behavior of the Maclaurin series. Then you get here something, okay. Then you get here a power series, okay, which in a certain domain of x, okay, is defined. And then try to prove that this object, that the power series represents the function, okay, at least at some domain which is smaller, okay, than smaller or equal, okay, than the domain where this power series is defined. Okay, you see, we are missing the last step, okay. Now, but maybe it's good to see once that if you at least draw. So what you're going to do is, okay, so what you have to prove in order to prove something like this is you look at the first n plus 1 terms here of this series. So this will give you a function. And what we have to prove is, okay, this function, okay, as n tends to infinity, converges to e to the x. Okay, as n tends to infinity, at least for some domain, for some domain like this for x. Okay, this is what we want to prove. Now we can first maybe check by Maple whether we really see a convergence. Of course, this is an easy example, and but maybe it's good at least for one example we should check out whether we, without proving it exactly, whether we can really see a convergence of this sequence of functions to this function here. Okay, so for the new students, okay, occasionally I'm showing demonstrations here in Maple, so you can also at the same time learn how to use Maple if you haven't used it before. Now, so what we want to do is we want to plot some of those functions we have seen, which are now behind, maybe, but we cannot see it anyway. So some of those functions, which I call Tn of x, which we for which we want to understand whether they converge to the function e to the x or not. So now the first one was this one. So normally if I want to plot more functions, I use these kind of brackets. Now Now the first one of these functions, t0 of x, is just a function 1. Then t1 of x would be 1 plus x. Then t2 of x would be 1 plus x square, 1 plus x square half. And let's maybe also t3 of x is 1 plus x square half plus x to the cube over 3 factorial, which is 6. Okay, so and I plot this over some region. Actually, I also want to see e to the x because this is what I expect to be the limit. And x is from let's say -1 to 1. Okay, now maybe I should remove some of them first. Maybe too many, and you do not know which one is which one because different colors. So maybe, so these are the first two. I cannot see my keyboard. Okay, so these are the first two. You see, you have now the red one. The red one is x is equal to 1, and the next one is the green one. The green one is the line 1 plus x. Now you see that. So what we want to do is, okay, we want to approximate the function which is the yellow one, e to the x, by a power series which is centered at 0. Okay. Now, of course, the function, the first polynomial t0 of x, okay, is already a good approximation only at the origin. Okay. And then you see as the polynomial, the degree of the polynomial is getting larger and larger. So in particular, the t1 of x seems to be already a better approximation of e to the x. Now, so the next one would be 1 plus x square half. So this would be the next one. This is now this should be the green one. The blue one is now so the new color is always for the last one. Okay. So you see now the blue one is e to the x, and you see the green one is already a better approximation for e to the x. And now as you increase the degree of the polynomial, so the next one would be this one. Now I take away the first two, and the last one is not over 3, it's over 6. Where is the mistake? This one. Okay, so you see now, now the yellow one is e to the x, and you see the green one is already a much better approximation, and so on and so forth. So, but if you plot this over a larger window, so let's say from -2 to 2, then you will see that there is still some even so you see that if I plot it like this here, so the yellow one is e to the x, and you see the others are approximations. So you see the approximation as the degree is getting higher and higher, is getting better and better around 0. But if you leave 0, okay, the approximation is not that good. But if you increase here, if you look at polynomials of a higher order, then you will see that okay, what you observe here, there seems to be convergence to the to our function. Okay. Now, and this is actually what we want to prove. Okay. So this roughly tells you this tells you okay that we can expect that the Maclaurin series for the function e to the x converges to the function. Okay, I could show you other examples, but now I don't have possibility. I don't have access to the blackboard, so for the other examples, we will just derive the Maclaurin series and then use the method to prove it. But you see here, this is I just wanted to show you this once for an easy example, e to the x. So the first thing, if you want to represent e to the x by power series, is you find the Maclaurin series, then you discuss the radius of convergence of the Maclaurin series, and then you try to prove convergence. And here for this example, you see that we expect that the series really converges for all x. So we do not have evidence for here and here, because the degree which we have chosen for the polynomial with which we approximate is not high enough. But also for such points, if for -3, if we make the degree larger and larger, what you can in fact see by drawing more graphs is that there seem to be convergence for all x. Okay, so we expect from what we have seen that this sequence here, Tn of x, converges to e to the x as n tends to infinity, and that this is true for all x. Now, and this is the next thing we want to prove. So actually what we have to do is, in order to prove this systematically, is we have to look at the error and between the function f of x and this Tn of x, and we have to prove that the error tends to 0. If the error tends to 0, then you will have that the representation holds for a certain interval. Now, this sequence of polynomials here has its own name. So this is called the Nth-Taylor polynomial. Okay, so the nth partial sum of the Taylor series is called the Nth-Taylor polynomial. Now, essentially, always if we want to prove convergence of a series, one of the methods is, okay, we look at the remainder. The remainder is defined as f of x minus Tn of x. Okay, and what we have to prove is, so Tn of x converges to f of x for all x with. Normally we prove this in some domain, like in some interval around the point A, if and only if, of course, Rn of x tends to 0 for all x with. Okay, so that, of course, this is trivial. This is also more or less one of the assignments we had, but not, of course, not for power series. Now, so what we want to prove is this here. Okay, so we want to take e to the x minus this one, and we want to show that we suspect for all x in R, okay, for a fixed x, this will always tend to 0. Now, in order to prove something like this here, what we normally need is some estimate for the error. Okay, and there are actually many different ways to estimate the error. The one we are going to use is called Taylor's inequality. Taylor's inequality is the following result. So if you know that the n plus first derivative is bounded in such an interval for x with the absolute value of x minus a is smaller than d, then the remainder can be bounded as follows. So m over n plus 1 factorial absolute value of x minus a to the n plus 1. And this is also true for x with absolute value of x minus a smaller than d. So this will give us, I will prove this next time, and in particular this will give us a tool how to prove that the remainder goes to 0 for a fixed x as n tends to infinity. And this will be our main tool in order to verify the third step of the 3 steps which I told you before, namely, once you have figured out the Maclaurin series and the convergence behavior of the Maclaurin series, the third step in order to complete your program of finding a power series representation for a given function will be to prove that the Maclaurin series on some domain represents the function. And for this here, we will use next time Taylor's inequality, and I show you then how to show that e to the x is equal to its Maclaurin series, which means then e to the x is equal to the series over n, x to the n over n factorial.